So let's continue with the third talk of this session, and Marcin Pilipczuk is giving the talk.
Thank you very much. So this is yet another paper by Vincent, and this time me and Michał, my brother Michał, and yet another paper on clustering. So welcome. This time on clustering, we'll be focusing on the facility location problem, which is slightly different than the one we heard in the previous slides. So we'll be in this problem. We have got clients and potential places for facilities, but now, and there's some metric on top of it, but now we are going again to open some facilities that correspond to like selecting the centers of the clusters in the previous talks, but now we are not have any like fixed bound on how many centers do we want, or or some like limit or soft limit or hard limit. This time every facility has got its opening cost. So that means that this is the cost needed to open this facility. And once you open some facilities, every client gets connected to the closest facility and then pay the total of like all the opening costs and all the connection costs. So there's like, there's no really any hard limit on the number of facilities, but you're opening more facilities incur more cost. Okay? And in these terms, this is the general setting I will be working in when every facility can have got its own different opening costs, but I don't have any real bound on number of opening costs, and I can open a lot of them if they are cheap. You can think of a special case when all opening costs are the same. This is like closer to this K-median problem we had before. That there's like the number of open facilities count, but the more you open, the less money you have to spend on the connection cost. You can think of capacitated. This is something we won't really use here, but I want just to mention here that every facility can have a cap on how many clients it can serve. And we heard in previous talks K-median when instead of opening cost, we had like a hard limit on how many facilities you can open, and you just count the connection cost later. Okay, so this is the problem we're working here, and we heard a lot about similar clustering problems. This is a clustering problem because it's really like you select which facilities you open, and then every facility gathers the closest clients around it, and this is the cluster of this facility. Okay, and we'll be working here. One thing that will be important for us is that in general metrics, we heard a lot about approximation lower bounds. For this particular case, we have got quite a small gap between the upper and lower bounds. For us, it will matter later that there's a constant approximation for this problem. We'll use it, but in general metrics, we have got quite a close understanding of what's the best approximation bound here. Okay? But we'll be working not in the general metrics, we'll be working in the planar graph metrics. So this is something slightly different than the Euclidean dimension 2 metric. Namely, we have a planar graph with edge weights, and some vertices of this planar graph are clients, some of these vertices of the planar graph are potential facilities. There can be many more vertices that are like Steiner points up there, or auxiliary points for connecting, and the distances are the shortest path in this graph. So we're working with a planar graph, which is something slightly more general than, something more general than planar dimension 2 Euclidean space. Okay, and the starting point of our work is the paper from Fox 3 years ago, when Cohen-Addad, Klein, and Matthew proved that actually, if you assume uniform cost, every facility has got the same cost, then you can get an approximation scheme, and this approximation scheme is actually quite simple. It's a local search with some, depending on the epsilon radius. Okay, and this actually works also for K-median there. But this one, so what we do, we just try to drop the uniform thing, and we manage to do it. So that's the main result of this paper, that if you assume non-uniform cost, there can be multiple costs for facilities, you still get a p-tas, and the dependency on epsilon gets a bit worse. We don't worry a bit much. But I want to mention here that there's another line of research going to better and better dependency on epsilon, and I want just to advertise the paper we had on ESA this year, which is different techniques. That's why I will just mention here that the thing from the previous slide can be actually get into efficient polynomial time approximation scheme. That means that there's a constant in front of epsilon, and then there's a polynomial in the end that doesn't depend on epsilon any longer. So that's like an advertisement of another like accompanying result we have. And now I'm going to focus on how to do this one, how to do facility location with non-uniform opening costs, how to do p-tas in planar graphs up there. Okay, that's the statement. Is the statement clear of what we are trying to do in the next few minutes? Good, thanks. Okay, so this is the outline of the algorithm. We start with some simple preprocessing, which I don't get much into it. This is something standard, and everybody of you can easily figure out how to do it, how to round some things and scale some things so that the weights and opening costs are actually integers bounded polynomially, positive integers bounded polynomially in the size of the graph. And the main trick, or the main initial trick, is to actually look at the approximate solution, but for not the original instance, but let's pretend for a while that all the facilities are cheap, that all the facilities get opening costs scaled by epsilon. So they're super cheap. So we are going to open in this approximate solution much more facilities than the supposed optimal solution is going to open. And what we are going to prove of this in the clusters, we are going to look at the clusters of this approximate solution with this scaled cost, and we are going to prove a number of properties that actually, this clustering that this approximate solution gives us, tells us something about what opt should do there. I mean, there will be some saying that this actually approximate solution is very good at connection cost, that this one actually points out more or less where the optimum will put facilities. We have got a lot of useful things. And then we look at these clusters and we put them on a log scale of a scale on the size of these clusters. There will be something called average cost, which corresponds to more or less the radius of the cluster. And we'll say that the clusters with very different average costs don't interact much with each other. So we're going to do a Baker layering argument on log scale of the average cost of the clusters, and that will be the main trick. And then once we get clusters of more or less the same average cost, this will be a standard but quite hard exercise for graduate student to actually nail down Baker, DP3 with DP3 with DP to end up with the pitas in the end. Okay, so that's the outline. So let us focus on the main parts, 2 and 3, approximate solution and analysis of the clusters for a moment now. So what we are going to do, let's now repeat it. We are going to do constant approximation algorithm, but we are going to feed this algorithm with opening cost scaled by epsilon. So opening is super cheap. I mean, not super, but scaled by epsilon. And we are trying to find the approximate solution. And then in the end, we do some regularization, more we're going to greedily first open facilities that still decrease the cost. I mean, so we are going to maximal. And then in the end, close facilities that have got empty cluster that no clients connect there. So all the steps decrease the cost, so there we won't loop in them. We can do it. And there. And first, because we scaled down opening cost by epsilon, and then suddenly, hey, but let's go to the original instance and let's look how good this solution is with the original instance, because we did constant approximation of the scaled opening cost. This is actually 1 over epsilon approximation to the original instance. That's to the original instance. And the second thing is that what I want to say here, what I advertised earlier, is that this approximate solution, I mean, because it opens facilities for very, very cheaply, it's very good at optimizing connection cost. What does it mean? I want to say the following lemma, which is, I won't prove here, but it's not very hard to prove, is that whatever you choose your favorite set of clients you care about, this thing, how it pays for connecting these guys, is not much more than what the optimum solution pays. I mean, this is just the lemma, and this lemma can be easily proven to saying that if this is not true, then there's actually some facility of the opening cost that if you open with this scaled cost by epsilon, you actually decrease the connection cost of the approximate solution. So that would violate our local search setup here. So we have got the solution that, okay, overpays 1 over epsilon, and mostly because it overpays the opening. I mean, it thinks the opening costs are much smaller than they actually are, but the solution is very good at connection costs. For any set of clients, it never overpays the connection cost compared to the optimum solution. And there's some error term, epsilon opt, cost of opt. Okay? So now let's look at the analysis of a single cluster. So we look at one guy from this approximate solution, and we look at its cluster. So this is you think you opened clusters, and you think of a Voronoi diagram in this graph of this opened clusters, of open facilities. And this is how these clients connect to the facilities, because they always connect to the closest facility. And I think of the radius of the cluster, the average cost of the cluster, is just I look at the total cost of this cluster in the original instance without the opening cost scaled down. So I take all the connection costs and take all the opening costs, and I spread it out evenly between the clients. So this is 1 over this number of clients connected to this guy. Okay, so this is the average cost, what on average is paid by every guy in the cluster. if I do the normal opening times, not the cheap opening costs, but the normal ones. Okay? And one property that's easy to observe here is that the optimum solution needs to open a facility within a radius twice the optimum cost. Because if in this big ball twice the average cost, there's no optimum solution, there's no guy from the optimum solution, then a guy from this cluster in average in the optimum solution travels more than average cost, which means that if you open this facility up there, you will get a cheaper solution. That's like the argumentation, you can do the math, but the intuition is here that actually here in this cluster, the average cost is this one, but if the blue one, there's no optimum solution inside this one, then on average you travel more than average cost, which means that you could afford instead opening this guy up here instead of connecting to somebody far away. Okay, so this cluster, this is the radius, and the intuition about this radius is that, I mean, within twice this radius, this average cost, you get somebody from the optimum solution. That's the property we'll be going to use later. Okay, and also because recall that this solution is like 1 over epsilon approximate solution, which means that if, and the average cost is like the average cost per client in this cluster, okay? Which means that which means that this quantity, epsilon squared times the average cost per client, is something like cheap. It's super cheap, it's for free, because this totals over all clients, this totals to epsilon opt, yeah? Because I'm 1 over epsilon approximation here, okay? So, I mean, every client has got this freedom of epsilon times average cost, epsilon squared times average cost to wiggling around, and this totals to epsilon opt. That means that, I mean, in particular, I can take the ball of radius epsilon squared average cost from the center and just move these guys away from this range so that I will clear up the area around up there. That will be useful in the future. Okay? So I'm clearing up the area in the center. Okay? But so there's the close clients, the guys that were very close, and I can move them away. But remember this intuition that epsilon squared times average cost is something you can afford per client to pay, and that's not a big deal. Okay? So so I moved this guy up there. Now let's look at the far client. So we have got this property. We'll go to here that I scaled down the picture. So this is like this twice average cost radius. There's some optimal solution up here. But there's some client far away, and actually this picture is wrong. Actually, this client should be in this cell, yeah? I mean, this client is in this cell, and this cell is really stretched away so that there's a client 1 over epsilon squared times the average cost. So now I'm looking not at the clients very close to the things, but I'm looking at the clients very far, that are like super far compared to the average cost of this thing from the center. And what I'm saying here is that I have got this property too, okay? This property 2 says that if I look at all the far clients, so I now set S to be all the far clients in all clusters. All the far clients in these all clusters, in optimum solution, they don't pay less in the connection cost than they pay in the approximate solution. That's what this one says. But in the approximate solution, they pay a lot. They pay like average cost of clusters over epsilon square. And I have got the property that there's somebody from the optimum solution close here, like twice average cost. So this twice average cost is like tiny compared to this 1 over epsilon squared times the average cost, which means that this guy in the optimum solution, it cannot pay much more than what he pays in the approximate solution, because he can go to the blue instead of the red in the optimum solution. Maybe there's a center much closer in the optimum solution, but there's one which is like comparable to the one in the approximate solution. So the punchline here is that the property says us that the approximate solution doesn't overpay in the connection costs of the far guys, but on the other hand, the existence of this blue guy says the other way around, that the optimal solution doesn't overpay, is not much more than what we pay in the approximate solution. So actually, these numbers and these numbers are very close if you take S to be the set of our far clients, which means that you can essentially ignore the far clients. You understood them already. I mean, the far clients are connected by roughly this cost to the thing. There is somebody in this thing by property 3 in this circle, which means that you can essentially ignore them. I mean, technically speaking, you need to be careful just to ensure that this blue guy is still there really in your solution we find in the end. But the punchline here is that you can ignore the far clients. I mean, you know how much you can pay. You can offset it at this moment and just forget these guys. Okay? So what we get here, we get these clusters with these average costs. This is still 1 over epsilon approximation, or we didn't change it much in the process. We know that opt needs to open something within the radius twice the average cost, and there's like a constant stretch of distances from the center. Like the distances from the center is like epsilon to the 4 stretch around the average cost up there. Okay, so that's the property we got of the clusters. And now we're going to rely mostly on the property 3 to do some sort of Baker layering. So let's look at these clusters. Let's look at this clusters, this approximate solution. And let's like put them on a log scale of the average costs. So this is like a log scale of their average costs. I mean, it's like in this direction because that's the exponent, but you think of this average cost decreasing as you go right, epsilon is small. You look at this log scale, and you look at this log scale, and because this was 1 over epsilon approximation, we need to do like Baker layering with epsilon square, 1 over epsilon square modulus. So we do 1 over, we set Q to be 1 over epsilon square, and we choose 1 every 1 over epsilon square, 1 over Q segment here on this log scale, and say that we are buying these facilities. So we choose the offset that's the cheapest in the approximate solution. That's like the standard like Baker layering approach. And we choose the cheapest offset with the minimum cost in the approximate solution. And because we have got like 1 over epsilon squared to choose one, this was 1 over epsilon approximation. We pay only epsilon opt to buy them, and we just buy facilities and connect clients as in the approximate solution up there. What we get here in the end, we get here that, okay, we do this opening here, and now on this log scale, this is the log scale, on this log scale, there are this like segments of facilities from the approximate solution that have got different, average cost, and they're like comparable here, they're within constant stretch, and there's a gap. There's no facility with that average cost. And there's a segment of facilities with some average cost, and there's a gap. And now the punchline is, like, we can define like Wi to be the facilities there, clients in this clusters to be Ri. And the intuition now here is that if I look at this facilities here and clusters here, these facilities and clusters are like super tiny. I mean, they're like epsilon to something tinier than the previous ones, okay? So they're like super tiny, which means that you can travel within, I mean, you can offset traveling within one of these tiny clusters to the average cost of the larger cluster. Okay? That means that you can travel out. That means that the facilities, the clients and facilities here don't really care what's happening in the small ones. They're going only to rely on the property free, that there is something opened within the twice average cost from the center, and they don't really care what is opened. I mean, whatever is opened there, whenever they connect here within this radius twice average cost, it doesn't really matter. Traveling across this twice average cost of this tiny cluster is something like for free or like super cheap. So here, what we really care, like from the smaller clusters, is that, I mean, we only have this promise that there's one open facility, which we can mimic by setting one facility for free opened up there, and we just resolve this instance like going from like largest to the smallest one, pretending that for the smallest instances, the only information we care about is that there's at least one open facility within twice average cost inside every cluster, and that's all we need to care. So this provides some isolation that you can solve these areas independently. You can solve the clusters and facilities independently for all scale of the like size of average cost. Okay, so the punchline we get here is that okay, we have got within each instance, within each one of these blue segments, if you look at all the clusters up there, the stretch of average cost is bounded by some function of epsilon. This is like this double exponential epsilon we get in the running time, and in each cluster, like there's this constant stretch between the distance from the center of the clusters. Okay. And if you get this one, then, I mean, this is like, because I'm 2 minutes left, this is exactly the moment when I want to say that, this is now an advanced exercise for graduate student here, up there. I mean, in this area. I mean, now if you have got this constant stretch, you do some now classic Baker with distances, like when one ring in the Baker is like a constant number of clusters, up there, a constant number of clusters. You buy some clusters, and there's some isolation. You can argue that you will never travel through too many other clusters in this setting. And then you get bounded radius of the instance. I mean, bounded radius in the epsilon and the maximum average cost in one instance. Remember that average costs have got bounded strength here. And then with this one, you just do classic dynamic programming over 3D composition on every bug is like 3 shortest paths. This is like quite standard planar graphs, and you do portals there, compute how many portals you need for what, for the precision you need, and do a few tricks with the DP states up there to have pitas, not eq-pitas. There's some care needed here. Okay, so I'm done. I have got 1 minute left, so I'll summarize with having, okay, this is our result here. There's a pitas for uniform facility location. I advertised the accompanying paper at ISA that for uniform facility location, you actually got dependency on epsilon as a constant in front, so this is efficient pitas. And I want to conclude with an open problem that, okay, we heard that the The Fox -3, I mean the Fox 2016 paper have got facilitated local search also for K-median, and I would like to ask about efficient pitas there. Thanks.
So, do you have questions? There is, well, we can use a couple of minutes. Yes.
I just skimmed over it because I didn't think this is that super tricky as that like new innovative up there. What I'm doing here is that I'm looking at the possible maximum average cost, and I'm doing like just BFS from one vertex, like shortest path tree actually from one vertex, and think of one ring of my bakers like things. I mean, the thickness of the one radius is like some large constant times the maximum possible average cost. And the intuition is that if you look at one such ring, you can argue that a client would never travel this ring from inside to the outside or the other way around. It's too thick. I mean, there's always an optimum solution guy closer to it. So if you do Baker for that one, so you buy every 1/epsilon² layer, you pay little, by the same argument previously, and you have some isolation that between the rings, between the things you bought, the client will never cross the ring you bought. So you have got now bounded radius if you do this one, so if you contract the inside up there. Okay, and this is like the punchline. And then with this one, you do like from this center, from this like root of your BFS, you do shortest path tree, and you do tree decomposition on every back is the shortest path tree, and then you argue that this precision of portals, this number of portals per shortest path is enough because of the constant stretch of the average cost is enough for the precision you need, and then you need to define dynamic programming states for the portals. I mean, what's the closest facility, how many clients connect here, et cetera, et cetera. And there's some arguments that neighboring portals don't differ much in their state, and that's how you get polynomial number of states, not quasi-polynomial. Okay, that was a 2-minute version of these 2 slides.
So I guess we can thank the speaker again. And